all the nodes on the right hand side of the root, they are greater than that. So because of this, what happens? Whenever you want to search any particular node from a tree, it can be retrieved in a less time complexity. But now we can think like why the name given to such type of tree is red black tree. So you first need to understand what is the exact difference between the previous trees which we have studied and this red black tree which we are going to study. Okay, now in binary search tree, what happened? Searching operation was made linear. I say that average number of comparisons required in binary search tree are big O of average. I said average, but you know, in worst case it can go up to big O of H. And what is H here? H is number of levels, or you can say height of your binary search tree. So sometimes it can happen. So if your binary search tree is a strictly binary tree, searching operation is guaranteed in big O of log n, because strictly binary tree is always height balanced tree, right? But now worst case can be if your binary search tree is left skewed or right skewed, then in that case you will require more number of comparisons, that is big O of H, wherein H equal to height of your binary search tree. So big O of H is a big number if you consider time complexity, right? So that's the reason why we have came up with a new type of tree, that is AVL tree. But now in AVL tree also we have, came across one disadvantage, that is whenever we insert a new number in AVL tree, every time we need to check balance factor of a tree, and if balance factor of some particular node is greater than -1, 1 or 0, then therein we need to apply rotation. So we know that if 10 numbers are given, then multiple number of times we need to apply rotation. So I have told you disadvantage of binary search tree also, because in BST, worst case searching time complexity is big O of H, wherein H is height of the binary search tree. And it will happen because sometimes your binary search tree is left skewed or sometimes it is right skewed. In AVL tree, what is the disadvantage? Disadvantage of AVL tree is that it requires multiple rotations. So every time I insert new element in AVL tree, I need to check for balance factor of each node and apply suitable rotation whichever is applicable. So we know 4 types of rotation we need to apply there. Okay. Now these are the disadvantage with this BST and AVL tree. That's the reason why these red black trees came into picture. Now first of all, let us try to resolve the history behind the name. Now red black trees are called as red black tree because each of the node in this red black tree is either red or black. So whatever nodes belongs to a red black tree, they will be either red in color or they will be black in color. That's why the name given to tree is red black tree. So if you want to introduce yourself with red black tree, just remember that red black tree is a binary search tree again, in which every node is red or black, and it is a type of self-balancing binary search tree. So when I say self-balancing, whether magic is going to happen over there, there won't be any magic. Of course, like rotation, we need to apply rotations over here, and one more operation is added in red black tree, that is called as recoloring of a node. Now only two colors are allowed, red and black. So if I say recolor red color, so of course red will be converted into black, and if I'm recoloring black node, it will be converted into red node, right? So recoloring, what it means? Simply, if it is red, make it black, and vice versa. If it is black, make it red. So in red black tree, you are offered with only two types of operation, that is rotation and recoloring. Then few of you might be thinking, rotations, they were there in AVL tree also. So if they are added in red black tree, what's the new thing? Is it going to be same as AVL tree? No. So this is what makes a difference for red black tree. So remember that in red black tree, maximum 2 rotations and sometimes recoloring is required. Now, even though see it is written maximum 2 rotation, don't interpret it literally as only 2 rotations will be needed, but we can comment it like in red black tree, number of rotations required, they are less as compared to your avial tree. Okay, so when I talk about rotation for red black tree, it is going to be less than your avial tree. And one more new operation is added over here, that is called as recoloring. So recoloring I already talked about. If node is red, make it black. If node is black, make it red. Okay, so red black tree is a roughly height balanced tree. Now, why I'm saying roughly height balanced tree? Because it's not mandatory that every time balance factor of node must be -1, 1 or 0. So it's not required in red black tree. Please try to understand this different. Red black tree is binary search tree. Very fine. But in red black tree, we need not to have balance factor of each node as 1, -1 or 0. Why we are saying roughly height balanced tree? Because some of the nodes in your red black tree are balanced. That's why we are saying that it is roughly height balanced tree. And what it guarantees? It guarantees all the operation including insertion, deletion, and go on. So that is the very important thing to note about red black tree. It will guarantee all operations in big O of log n time. Okay, then you can say that the unit name is, we know the name of unit is search tree, and in this search tree we have seen what is static tree table, what's dynamic tree table, and then we tried to analyze how OBST and then how AVL tree, they can be used to store a big data in a form of static and dynamic tree table. Then we can think, or many of you might be feeling like, why so many types of trees are needed? So which type of tree to be used, it will depend on what? It will depend on the situation. Now situation means what? In what kind of application you are going to use that tree. So which tree, where I should use AVL tree, I need to look for a proper application. Where should I use OBST? The place where I want to find a tree with a minimum cost. So therein I will go for OBST. Okay, so which type of tree we should use where? It will depend on the application, or it will depend on the situation. So I hope with this you have got at least introduction about red black tree. So it is some tree which is binary search tree only, because here also left nodes will be smaller than the root and right nodes will be greater than the root. And the main thing to note here is every node will be a colored node. So node colors can be red or black, and it is type of self-balancing binary search tree offering two operations called as rotation operation and recoloring operation. Okay, and I have also told you why red black trees are invented and how every tree is having its own uniqueness, how AVL trees are different, how OBST is different. Okay, and now we will look like what is there in the red black tree. Okay, so I hope at least you have got introduction to the red black tree. Now here are some properties of red black tree which we need to remember. Okay, so these are the properties. Please follow my mouse pointer. So these are the properties of red black tree. I am telling you again, this is little bit not complicated, but little bit confusing topic to understand. So again, I am telling, if you follow your local author book, you will not understand this topic. Okay, I guarantee this to you. So it will be better. Anyway, you all have joined, so it will be better if you are, concentrating on what I am saying. Because once you understand the concept, then it will be helpful for you for your further learnings. Okay. Now these are the properties of red black tree. What happens in red black tree? Root is always black. Now we all know that in one tree there is always one root. So remember that root of tree is always black. Then next, all the leaf nodes are black. So I have written one more word here, that is null pointer. So we know that leaf nodes are further, they are having null pointers. So we have seen the concept of extended binary search tree. What is extended binary search tree? Leaf node, they have further pointers which are called as null pointer. So that is what I mean here. All the null pointers in red black tree are black in color. Okay, then third property of red black tree is if node is red, then its children are black. So if a parent node is red, then of course all its children will be black in color. And then the next property is every path from a node to any of its descendant. So every path from a node to any of its descendant nil node has same number of black node. So now to justify this, I will show you this particular PPT wherein a tree is drawn, which is the red black tree, and let us try to analyze these properties which we have just discussed. Okay, so let us go one by one. So it is binary search tree, already I told, satisfying every node is either red or black. So we know that root is always black. So you look at any red black tree, the main root of the tree will always black in color. Now how to remember this? See, we can see, we can, have an analogy like consider root. Now if we look at our family, now who is root of our family? Our grandparent. Just a minute. माझा क्लास चालू आहे, मी कॉल बॅक करते. क्लास चालू आहे, मी फोन करते. So in our family, who is there at the root? Our grandparents are there at the root, and and we all are descendants. So being descendants or being successors, we always get angry. Or you can see that our grandparents and all our other members in family, they are very calm. So we can say, we can like compare this like black is a color showing calmness property, and red is a color showing angriness property. Okay, so how to remember that parent should be black? So we can just compare it with like grandparents in the family, and they are always calm, and other people in family, they used to get angry, that's why they are red in color. So remember this like this analogy which I have just discussed. So parent is root is always going to be black, and its children, they are red in color. Okay, fine. So every leaf is nil and is black. Now what I want to tell here by using a leaf node. So these are the leaf nodes. See, 1 is leaf, 6 is leaf. So this property doesn't mean that 1, 6, 11, 15, 22, 27 should be black in color. No. So what I mean by leaf here, this is the last node in this particular path, 13, 8 and 1. So we, in our general terminology, we say it as a leaf. But if we consider the extended binary search tree, then all the null pointers are replaced by this nil. So how you should try to remember this thing? All the null pointers are always black in color. Okay, all the null pointers are always black in color. Null pointers are also called as nil pointers. So all the nil pointers you can see here, even downside also I have few pointers, they are black in color, but my taskbar is coming in between, that's why you are not able to see them. So just remember all the nil pointers, they are black in color. Now the next property to observe here is if node is red, then both of its children are black. So you can see that 8 is here. Both of the children of 8, that is 1 and 11, are black in color. I have 17 here. Both of the children 15 and 25, they are black in color. So nodes, if a parent is red, then its children nodes are black in color. Now go to the next property. For each node, all paths from node to descendant leaves contain same number of black node. Now let us try to analyze what is a path first. I need to minimize it. What is a path? Just follow my mouse pointer. So this is one path, 13, 8, 1, 2 nil. So this is one path. Okay. Then another path can be what? 13 to 8. Okay. Then 8 to 11, 11 to nil. Another path can be 13 to 8, 8 to 11, and again this 2 nil. Okay, so this is what you need to think about. So for each node, all the paths, like I have shown you some path, Path means what? You start from some node and try to reach to the nil node. Okay, so that is path. So begin with root and reach to the nil node. So what this property is telling you, on this path, all the paths, they will contain same number of black nodes. So you check any path, it contains same number of black nodes. Let us consider this path, 13 to 8, 8 to 11, and 11 to nil. So how many black nodes are there? 1, that is nil is 1, 11 is another, and 13 is third one. You check this another path towards the right branch again. So I have nil here, again I have 11 here, I have 13 here. So you may trace this path also, 13 to 17, 17 to 15. So how many black nodes are there? 13, 15, and this nil. Okay, go for the right branch again, 1 nil, 1 15, and other is 13. So you can check it for all the paths. Then you will come to know that all these paths from root to the leaf or nil node contain same number of black node. Okay, so these are the properties of red black tree which we must know before we perform any operation on red black tree. So I hope I have introduced you all with the red black tree. So let me know, do you have any doubt up to this? If you have any doubt up to this, then we can resolve that and then we can move further with insertion operation on red black tree. Any doubt up to this? Any doubt so far? Yes, no, confused? What? Aditya,
No,
any
ma'am.
doubt? No, ma'am. Okay, so one student have replied, that is fine for me, not a problem. We'll proceed further with the insertion operation on the red black tree. So it's an appeal. If you have a notebook and pen, please follow or try to solve example with me so that you will also understand it. And please be very careful and listen it with full concentration, then only it will have some meaning. Otherwise you see from where to learn and how to learn. Okay, so if you have understood these properties, then we come with 3 thumb rules for red black tree. What are the 3 thumb rules for red black tree? In red black tree, root is always okay. Then second property that we can come across for red black tree is no two adjacent red nodes can be there, because we have said na, if parent is red, then its children node are black. What is adjacent? Adjacent means what? Nodes which are directly connected to each other, and parent is directly connected to its children na. So if my parent is red, my property says that children will be black in color. So can we have two adjacent red nodes then? Never. Okay, we will never have two adjacent red node. So that's why second property of red black tree is we never have two adjacent red nodes. Okay, and third property I already told you, just we have discussed, count the number of black nodes in each path, they are always same. So if you trace any of the path in red black tree, you will always get same number of black nodes along each path. So these are the 3 thumb rules which we need to remember forever for red black tree. Okay, now these are the rules for insertion operation in binary, not binary search tree, on red black tree. So if I want to build a red black tree from a given sequence of numbers, I need to follow certain number of rules. Please try to understand each of the rules very carefully. Now what is rule number 1? Rule number 1 states that if tree is empty, create a new node as a root node with a color black. So this is but obvious na, because every time we have said that root is black in color. So this property is very simple. This first rule is very simple as we have already discussed it. Okay, so if tree is empty, of course a new node to be inserted will be inserted as a root node, and root is always black in color. So that's all. Then rule number 2. If tree is not empty, create a new node as a leaf node with color red. If your tree is not empty, then always a newly created node will have red color. This is very simple and easy to remember property. So if there is any node in a tree, then of course new node created will have red color. Remember this. Then third rule says that If parent of new node is black in color, then exit. Exit means what? You have done with insertion of that particular node in a tree. So whenever you insert any node in a tree, look at the color of parent. So if color of parent is black, then you don't need to apply, recoloring, rotation, nothing is required. Simply exit and go for insertion of the next number. So if a parent of new node is black in color, very nice, satisfied, just exit and go for insertion of a new node. Then the next and very frequently required rule number 4. If parent of new node is red, because we have already discussed na, if node is red, then its children must be in black color. But now what is happening here? The new node which we are creating if tree is not empty is always red. Okay, the new node which we are inserting in red black tree is always red in color. And now imagine you have just created a new node which is red in color and its parent is also red in color. So whether can we have two adjacent nodes with red color? That's not possible. Hai na? So that is what is written in rule number 4. So if parent of new node is red, then check color of parent's sibling. Now who are parents' sibling? Consider yourself. Okay, consider us. Now recall who is your parent. Recall your father. So parents' sibling means who? Uncle. Hai na? Parents' sibling means who? Our uncle. Right? For example, in family hierarchy, I am telling. So if parent of new node is red in color, then you need to check the color of parent's sibling. Now parent's sibling is also called as uncle of new node. So in your favorite book, they have used term uncle. But I think student will get confused like how uncle came in the data structure. So we call it as a parent sibling. Okay, so this is what if your parent is red in color, then you need to check color of parent sibling. So there are two possibilities when you look for the parent sibling color. Either color of parent sibling can be black or it can be red again. Hai na? So if color is black, म्हणजे parent sibling color, if it is black or null, black or null, it means what? Our parent don't have any sibling. आपले parent एकटेच आहे, they don't have any sibling. So these are the two possibilities which can have. हे काय डिस्कस करतोय रूल मध्ये आपण? इफ पॅरेंट ऑफ न्यू नोड इज रेड, then we need to look at the parent's sibling. Okay, so parent sibling, of course, again they can have two colors. They can have black color, they can have red color. किंवा असंही होऊ शकतं की पॅरेंटला सिबलिंगच नाहीये, आपले पॅरेंट एकटेच आहेत, है ना? So again A and B conditions are denoted over here. If color is black or null, if color is black means कोणीतरी आहे सिबलिंग आणि त्यांचं कलर ब्लॅक आहे. Or null. Null म्हणजे काय? There is no sibling. Our parent is alone. Okay. So if either is a case, then you need to apply suitable rotation and you need to recolor. So when I say recolor, you just need to convert the color. If it is red, make it black. If it is black, make it red. Recolor means what? You need to revert the color of the nodes. Okay. And this is B condition, which is telling you if color is red, means what? If parent's sibling color is red, then you simply need to recolor. Here you are not applying rotation operation on the tree. So if your parent sibling is red in color, simply recolor. So this will not do. Again you have to check the parent's parent. Parent's parent म्हणजे grandparent. Okay, you need to check the parent's parent of new node. And if it is not root node, then also you need to apply recolor operation on the grandparent, that is parent's parent. Okay, so I know that in first glance, you will not understand this rule number 4, but as and when we go through, inserting nodes one by one in red black tree, you will get it easily. Okay, so are you ready to apply or to build red black tree?
Yes, ma'am.
I think students are feeling hungry. Don't be hungry. I know your exams are approaching, and as per the guidelines given by department, we should conduct lecture only for today, I think, right? But I am telling tomorrow also I am going to conduct DSA class. I don't know about others, but DSA class will be conducted. Why? Because from this unit number 4, only simple concept of AA tree k-dimensional tree, and splay tree is remaining. So I am going to wind up this unit number 4 before your examination starts. Okay, so those who are interested and want to complete these topics will join. Others, about others, I don't care. Okay, so please remember, today also attendance is very less, but that really doesn't matters for me, because those who are needy or those who want to learn, they are already there in the class. So fine, without wasting a time, let us try to build red black tree. Okay, so be there with full attention, then only you will be able to understand. Now we know that red black tree is a binary search tree as well. So whenever you are inserting a new node in this red black tree, see that it is also satisfying properties of binary search tree. So first of all, you need to insert node 10. So we know that root always have a black color, no? So root is alone, root is king. So it will be inserted as a root and will have color as a black. Then next we have to insert 18. Now what our rule number 2 says, if tree is not empty, create a new node as a leaf node, and which color that new node should have? Every time you create a new node, it will be always red in color. So 18 you have created new node, and as this is binary search tree, you will compare 18 with 10, but 18 is greater than 10, so you have inserted 18 to the right hand side of the 10 and red in color. Okay, next you have to insert 7, so we compare 7 with 10. Which color 7 will have? Of course, tree is not empty, no? So every time you create a new node, it will have a red color. So I insert 7 to the left of 10 because it is smaller than 10. Next, I have to insert 15 in this tree. So where 15 will go? 15 is greater than 10. So must go on the right hand side. So there is 18. 18 is greater than 15. So my 15 must be there on the left hand side of the 18. Okay. But now what happened over here? I told that we cannot have two adjacent nodes as red nodes. Okay, but now this property has been violated. Na? Why? Because I have node 15 and 18, that is parent and child, and both are having red color, right? So here we have red parent child relationship. Now what to do when parent of new node is red? So this is rule number 4. So when this is the case, you have to look at the color of the parent's sibling. Now, who is parent of 15? 18 is parent. Okay. Look at the parent's sibling. So 15चं सिबलिंग कोण येईल बरं? 15चं सिबलिंग म्हणजे काय? जो नोड 18 ह्या पॅरेंट पासून डिराइव्ह झालेला आहे. बट नाउ वी कॅन सी हिअर that who is parent of 15, 18, and whether it is having any sibling. 18 is having any sibling. Who is sibling of node 18? Sibling means what? Those nodes who are derived from same parent. So see, 18's parent is who? 10. Whether 10 is having any other child?
7.
7. अरे साधी गोष्ट आहे बघा, जेव्हा जेव्हा रेड रेड रिलेशनशिप येते त्यावेळेस तुम्हाला काय करायचं आहे? पॅरेंटच्या सिबलिंग कडे बघायचंय. ओके, पॅरेंटचं सिबलिंग है ना. मग आपलं पॅरेंट कोण आहे इथं? 18 आणि 18चं सिबलिंग. सिबलिंग या शब्दाचा अर्थ काय होतो? असे नोड एकाच पॅरेंट पासून डिराइव्ह झालेले आहेत. ओके, सो हु इज सिबलिंग ऑफ 18? 7. 7 इज अ सिबलिंग ऑफ 18. ठीक आहे, मग सिबलिंग कडे बघितल्यानंतर दोन पॉसिबिलिटी असू शकता. तुमचं जे सिबलिंग आहे ते ब्लॅक कलर मध्ये आहे किंवा रेड कलर मध्ये. मग सिबलिंगचं कलर जर ब्लॅक असेल किंवा सिबलिंगच नसेल म्हणजे नल असेल तर यू नीड टू अप्लाय रोटेशन आणि रिकलर. पण जर त्या सिबलिंगचा कलर रेड असेल तर वी सिम्पली रिकलर म्हणजे त्या नोडचं कलर चेंज करायचं आणि परत पॅरेंटचं सुद्धा कलर चेक करायचं. पॅरेंट जर रूट नसेल तर त्याचा सुद्धा कलर रिकलर करत चालायचं. ओके, सो this is the thing which we need to discuss here. So 15's parent is 18, 18's sibling is 7. As 7 is red in color, याचा कलर रेड आहे. मग कलर जर रेड आहे तर आपल्याला इथं रोटेशन अप्लाय करायला लागेल का आपल्याला? नो, वी डोंट नीड टू अप्लाय रोटेशन हिअर. वी जस्ट नीड टू रिकलर. a parent and its sibling. मग पॅरेंट कोण आहे आपलं? हु इज अ पॅरेंट? 18. And who is the sibling of 18? 7. So you can see here 18 and 7 they are recolored. आणि मग आधी ते रेड होते, आता रिकलर केल्यानंतर काय झाले? They are now black in color. What will happen with 15? Nothing will happen with 15 if sibling of parent is red in color. हे समजलं का? Are you getting what we have done here? Which rule we have applied here? Yes.
Yes, ma'am.
Which rule we have applied? Why this is not red black tree? Because we can see here two adjacent nodes are red in color. Whenever this is the case, you will look at the parent sibling. So parent sibling means what? Now if we consider 18, 7 is sibling. Siblings are derived from the same parent, right? So if your sibling is red in color, you simply need to recolor these two nodes. So initially they were red, now they are black. Okay, and your process doesn't stop over here. You also need to look at parents parent node. So who is newly inserted node? 15. Parents parent म्हणजे कोण झाला? 10. So if it is root node, then it's okay. Root is always black in color. पण जर parent node जर तुमचं black नाहीये तर त्याला सुद्धा आपल्याला रिकलर करत जावं लागतं. So this I will tell you in next step. Okay. Now next we have to insert 16. Can you tell me where 16 will be inserted? Please be fast. Where 16 will be inserted? This is binary search tree.
Right side of 15.
Right side of 15, because you compare this 16 with 10. Okay, 16 is greater, so must go in right. So we have 18, right? So it is smaller, so you will check with the next node, that is 15. 16 is greater than 15, so it will go on the right hand side. Everything is written, but you guys are not responding. I don't know what's the reason. So now what you have to do, if you look at the tree, this is not red black tree, because what has happened here, we have now two adjacent nodes 15 and 16 which are red in color. So again here red conflict has occurred. So what is a thumb rule? Whenever red conflict occur, we check at parents sibling. Okay, we check at parents sibling. आपलं parent कोण आहे 16 चा? 15. 15 चा सिबलिंग म्हणजे तो कुणाचा चाइल्ड असला पाहिजे 18 चा, है ना? पॅरेंटचं सिबलिंग म्हणजे कुणाचं चाइल्ड असलं पाहिजे 18 चा, है ना? बट यू कॅन सी हिअर नाउ 18 इज नॉट हॅव्हिंग एनी चाइल्ड, है ना? 18 ला दुसरं चाइल्ड आहे का इथे? नाही. म्हणजे इथं काय झालं? 18 ला जर चाइल्ड नाहीये तर आपलं कोणतं कंडिशन ट्रू झालं? इफ कलर इज ब्लॅक और नल. नल आहे ना आपल्या पॅरेंटला, आपला जो करंट नोड आहे त्याच्या सिबलिंग, त्याला जो पॅरेंट आहे त्याला सिबलिंगच नाहीये, है ना? म्हणजे आपल्याला काय करावं लागेल इथं? वी नीड टू अप्लाय रोटेशन अँड रिकलर. ओके, रोटेशन अँड रिकलर. तर रिकलर कुणाला करायचंय आणि रोटेशन कसं अप्लाय करायचंय? प्लीज जस्ट हॅव अ लुक ऑन दिस. सो we know how to handle this LR rotation. In LR, what we do? We fetch this node 16 on the left hand side. Can you please follow my mouse pointer? So if I stretch this 16 towards the left hand side, what will happen? Your tree will become like 18, left side 16, and again left will be 15. See, now you can see that position of 16 has been changed. Why position as 16 is changed? Because we also need to look that it is following properties of binary search tree. And we know that left nodes on the tree are always smaller than the root. Okay, so once you convert this into LL, and we know very well how to deal with LL rotation, so we simply rotate our tree clockwise, so that now 16 will become root and 15 will be the left node and 18 will be the right node. Okay, so in this case, while applying this LL rotation, you need to apply recoloring on these two upper node 16 आणि 18 ला तुम्हाला काय करायचंय? रिकलर. So you can see in the original tree, what was the color of 16? It was red. So now it will become black. So I have shown here it is recolored and initially it was red, now it is black. आणि 18चं कलर काय होतं आधी इथे ब्लॅक होतं, now also it is recolored from black to red. Okay, so this is how when your parent sibling is not there, if it is black or if it is not there, we take rotation also and we recolor suitable nodes also. Okay, so after applying rotation and recoloring operation, my new tree becomes like 10, 7, 16. 16 is black in color and children of 16 are red in color. Okay, so this is how node 16 can be inserted. Just I'm scrolling through so that you will understand. I'm damn sure that in one read you will not understand. You also need to go through on your own once again, okay, so that you will understand. Now next we have to insert 30. So it is very simple. We can easily guess where this 30 will be inserted. Because 30 is greater than root, we come towards the right side and we come to know that 30 is even greater than 18. So it will be inserted here. So this is the proper place for 30. Now what has happened here? See, for your understanding, I have written everything in detail here. I have written a complete rule over here. So now what is this? This is again red relationship. So when it is red, you need to do what? You need to look at the parent's sibling. Now who is sibling of 18? 15. 15 is sibling of 18, na? In this case, what you have to do? You just have to recolor. सो रिकलर केल्यानंतर काय होतील 15चं आणि 18चं कलर ब्लॅक होईल. ओके, आधी रेड होतं, आता काय होईल ब्लॅक होईल. एवढंच करून थांबायचं का नाही? एवढंच करून थांबायचं नाही. रिकलरिंग मध्ये आपल्याला पॅरेंटचं सुद्धा कलर बघायचंय. आता आपण 30 वर काम करतोय. 30चं पॅरेंट कोण आहे 18 आणि पॅरेंटचा पॅरेंट नोड म्हणजे झाला 16, ग्रँड पॅरेंट नोड. ओके, यू ऑल्सो नीड टू लुक ॲट द कलर ऑफ 16. मग हा 16 जर तुमचं रूट नोड असेल ना तर काही नाही करायचं त्याला. पण आता 16 रूट नोड आहे का इथे? 16 इज नॉट रूट नोड. रूट तर 10 आहे ना. मग जर हा पॅरेंटचा पॅरेंट जर रूट नसेल तर त्याला सुद्धा तुम्हाला रिकलर करायचं आहे. म्हणजे 16चं कलर जे इथं ब्लॅक आहे, रिकलर केल्यानंतर तुमचा 16 हा नोड काय होणार आहे? रेड होणार आहे. सो आय एम झूमिंग इन सो दॅट यू विल बी एबल टू सी बोथ द फिगर्स. बघा काय झालं, 15 आणि 18 रिकलर झाले कारण 15 हा 18चं सिबलिंग होता आणि 15चा कलर रेड होता म्हणून आपण त्यांना रिकलर केलं. सो 15 and 18 they are now black in color. And we also look at parents parent, that is grandparent. Grandparent is not root, so we are recoloring that. Initially it was black, now it is red in color. Okay, now I will explain one more condition and then I will share this PDF with you. You please go through remaining values and just try to analyze the tree on your own. Okay, now I have to insert 25. Okay, so where this 25 will be inserted? Of course on the left hand side of the 30. Now what happens again when I insert 25? Again it is red conflict. So every time it is red conflict, look at the parent's sibling. ओके, हु इज पॅरेंट 18. ओके, 30 ला सिबलिंग आहे का इथे? 30 हा राईट चाइल्ड आहे 18चा. 18 ला लेफ्ट चाइल्ड आहे का? नाहीये. म्हणजे इथं आपल्याला काय करावं लागणार? रोटेशन आणि रिकलर ऑपरेशन अप्लाय करावं लागणार. कोणतं रोटेशन लावायचंय? इथं दिसतंय ना आपल्याला 25 कुठं? 30च्या लेफ्टला. 30 कुठं आहे? 18च्या राईटला. म्हणजे विच टाइप ऑफ रोटेशन? दिस इज RL rotation. So when we need to apply RL rotation, we convert our tree into RR tree first. So while converting it into RR, you should also take care that it is binary search tree, है ना? So how your RR will become? It will become 18, 25 and 30. 18, 25 and 30. You can observe that all the right nodes, they are greater than the parent. Okay, and if you now you know that how to deal with RR. If it is RR, we just fold our tree towards the left side. So anti-clockwise rotation has to be performed. So that's why 25 will become the root, 18 will be there on the left side and 30 will be there on the right hand side. Okay, so only rotation will do. No, in your this RR, upper two nodes must be recolored. म्हणजे 18 आणि 25. इथे सुद्धा LL मध्ये आपण काय केले होते? वरचे दोन नोड जे होते ते रिकलर केले होते, है ना? इथे 18 आणि 16 ला. यू कॅन सी 18 आणि 16. 18 and 16 we have recolored. In the same way here also, कुठं गेलं ते? Okay, in the same way here also you need to recolor your 18 and 25. So you can check 18 चा color काय होतं original tree मध्ये. 18 was black in color, so now it will be recolored, it will be red. Okay, आणि 18 सोबत तुम्हाला कोणाला करायचं आहे 25 ला. So 25 was red in color, now it is black. म्हणजे तुमचं ट्री कसं येईल. So see, upper part will remain same ना. 10 left will be 7, then 16 and 16 left will remain 15. फक्त इकडं जिथं गडबड होत होती तिथं आता आपल्याला हे करायचंय ना 25, 18 आणि 30 है ना. 25, 18 and 30 and we have to apply recoloring also on 18 and 25. So this is how your tree will look like after applying rotation and recoloring. Okay, are you getting? अजून एक सांगू का पुढचे एखादं इन्सर्शन सांगू की थांबायचं तुम्ही बघून घेताल. यू टेल मी व्हॉट टू डू. Should I go for one more case and then we will stop, or you will do it on your own because I have discussed all the cases. So you tell me if you require my help, then I will do that. Otherwise we will stop. You tell me what to do. Be fast. I am also hungry. I also need to take my lunch. My family members are waiting for me. So be fast. Tell me what to do. Should I take one more case? तुमचे शब्द एवढे महाग असतील असं वाटलं नव्हतं मला है ना. फॅकल्टीज दे आर गोइंग ऑन speaking for 1 hour continuously. They are talking. If we ask you yes or no, that also you are not speaking out. What to do? Should I stop then?
Yes, ma'am.
Okay, so you will do on your own. You will go through this example. Promise me that you will go through this example. Will you?
Yes, ma'am.
ओके,
Yes,
यस
ma'am.
म्हणाली ती, पण मग एक एक्झाम्पल घेण्यासाठी हो म्हणाली की थांबण्यासाठी हो म्हणाली तेच नाही का आलं मला. धनश्री काय करायचं कळतंय का? शुड वी स्टॉप?
Yes, ma'am.
Okay, fine. So I will not get into one more case. Okay, so I hope you have understood. If you have not understood, please go through the notes which will be given by me for one more time. Okay, and then you will understand it. But please remember that this is the only process how red black